speed up according to the number of FPUs. So what we did is to really approach this line, and here at the left side, right-hand side of the diagram, you can see that we overreached this red line, because the calculation here is specific in terms that it's not really fully floating point, but also has many branches. All those states, their transitions. We have branches, and integer units are also employed. So the truth is somewhere in between, as you can see. So what would be our conclusion for this? We reached our goal. The order of magnitude of using available hardware, of course, is there, and it's really scalable. Using nowadays hardware, it is not that easy, and it's not very straightforward to handle these measurements or referential measures for parallel algorithm goodness. Thank you. That would be it.
Thank you very much, Milos. Questions? So actually, can you turn the last? So the red color is what column?
No, it was mentioned like column P, but it's perfect speed up according to the number of available floating point units within processors, not integer units.
Okay.
We have twice integer units, then we have floating point units.
So the real clustering is actually 120 processors, 40, 50, 60 times, right?
Yeah.
Okay, so it's not so bad. So that's dependent from the number of data or dependent from number of calculations? Speed up.
Speed up here is dependent more on there is a law in parallel computing that more data we have greater speed ups. So it's largely dependent on number of data of our units, of our filaments or TM units.
Okay. Any questions? Thank you very much again. Now we have next speaker, Dr. Miljan Milošević. Dr. Miljan Milošević from BioRC, Bioengineering Research and Development Center. He received Master in 2008, PhD 2012, Mechanical Engineering at Faculty of Engineering, University of Kragujevac. He is currently working as a Research Associate at the Research and Development Center for Bioengineering in Kragujevac. He participates in the project of Serbian Ministry of Science, Multiscale Modeling Biomedicine, and ARTERY project, Multi-Level Patient-Specific Arteriogenesis Model for Outcome Prediction Decision, Support Treatment and Virtual Handle Training. His research interest is focused on numeric modeling of diffusion process, computer modeling in bioengineering and solid fluid interaction problems. Using FF method, Dr. Milošević is author and co-author of 9 publications in international and national journals and 7 international conference publications. Please begin.
Thank you for the introduction. Hello to everyone. As you can see, I will today talk about modeling of diffusion in complex system. First of all, I want to say that this research is done in collaboration with the Research Institute of Methodist Hospital in Houston, and the leader of this project is Professor Miloš Ković. He is corresponding member of Serbian Academy of Science and Art, and coordinator of this project is Dr. Arturas Iziemos. He is a research associate of this research institute in Houston. First of all, I want to say something about our motivation. So we want to, our motivation is to development of methodology and software for numeric modeling of molecular transport in complex media. our focus is on drug delivery in cancer tissue, diffusion through capillary walls, blood vessels, etc., and diffusion in extracellular space. On this slide, I will try to explain everything we did in our research. First of all, it has to be mentioned that diffusion is a very common and most important process in all natural, technological, and biological systems. Some of examples are photosynthesis in plants, gas exchange in the human body, drug delivery, and so on and so on. And in common continuum theories, the most fundamental law is Fick's law. But in complex media, where, for example, on this second picture, we have some molecule which is moving in the space, and there is some geometry which have to go around. This molecule have to go around this surface, but also there is some chemical interaction between this surface and molecule, and this interaction is not included in this Fick's law. So we have to think about new methodology which has to take this surface interaction into account. We apply molecular dynamic simulation to calculate this surface interaction. So molecular dynamic is a well-known tool for molecular design, but this molecular dynamic is not practical for bigger domains. MD is practical just for small domains, order of nanometers. So despite we have a system of a million of molecules, we cannot model big systems. So we have to apply another concept. Of course, we are dealing with finite element method. Finite element method is a well-known continuum modeling method, but this method don't have incorporated these surface effects. And one of the way to take these surface effects into account is to couple finite element method and MD method in some multi-scale method, and we developed this hierarchical model which couples FEM and MD in that way that we calculate these surface effects using MD, and then those scaling functions, which is dependence from the wall, distance from the wall, and we incorporate these effects into FEM and do a calculation. You will see at some of the next slides that we validated our concept on some simple nanochannels. So that encouraged us to think about some complex model. At the end, we tried to model diffusion in some complex systems. We do modeling of some fibers, spheres, and we try to get better explanation of this diffusion process. Also, Professor Kojic developed this new numerical optimization method, and you will see how it is done. Okay, on this slide I just want to mention some basic relations. So Fick's law, we use Fick's law in our models, and we use equation of mass balance for some reference volume within some diffusion domain. Something about ND simulations. So these ND simulations are done in Houston, done by Professor Arturo Zienus. In order to mimic some nanochannel, he has some silica slab in between two water slabs, and we have these particles are molecules of glucose. So he ran MD simulation, and these molecules are moving in the space, and how to use this movement of molecules. He used RMSD method, and he got these diagrams. It is a dependence of diffusivity from the distance from the surface. So if you can see from this picture, if we are close to the surface, distance between 0 and 1, then there is some attractive forces from the surface, so movement is constrained. If we are long enough from the surface, for example, at 4 nanometers, this molecule is far enough from the surface and it is not affected from the surface, so he is free. He is free to diffuse in the system. Okay, we are using FEM. These are just some basic relations. So we are starting from mass balance equation. We started from mass balance equation, and after that we are using the Larkin procedure, and we transform this mass balance equation into iterative incremental procedure, and these are just parts of this matrices in equation we are using in our software for numeric modeling. Okay, here I will say something about our hierarchical model and how we incorporate this scaling function. So, using MD simulation, we have this diffusivity distance dependence. So, if we normalize, we have this. We have 4 curves for some 4 different concentration. This different concentration means that we have a different number of particles in our MD model. And if we normalize these values to the bulk value, which is bulk value, as I said, is far away from the surface where there is no surface effect, we can get these 2 diagrams. We have scaling functions, which scaling function depends on distance from the surface, and we have dependence of diffusivity from the concentration. And how we use it in our FEM model, for example, we have some FEM domain, we have a wall, and we have some point P, which is on distance h from the wall. So for this point P, we first find the concentration from previous time step. Using this diagram, which is also here, we can calculate bulk diffusion coefficient, D of C, for that concentration. So that is our D bulk. And then using these scaling functions, for this point P, we know h from the surface, and we have sets of the curves, and we can, using some interpolation, we can calculate a scaling function. And finally, we found diffusion coefficient as scaling function multiplies D bulk. We did the validation of our hierarchical model. We've published 2 papers in some international journals, and those validations encouraged us to start thinking about modeling of diffusion in some complex mediums. So, for example, if we have some fibrous medium, which can be extracellular matrix, some tissue. So we from this large domain we can take just one reference volume surrounding the point P, and this reference volume is our microstructural model. So it is of cubic shape. So we use this reference volume and we calculate the diffusion for this reference volume. We have fibers, real fibers inside this reference volume, and for example, for some point A, who is in this reference volume, we find closest fiber, and we find the distance from that closest fiber, and using the scaling functions from previous slide, we can calculate diffusion coefficient for that point. And then we calculate the diffusion for whole system. A characteristic of diffusion is mass release curve, which tell us how the mass is changing in the time. This is that homogenization procedure I was talking about. And what is the point? So we have microstructural model, which is real model with fibers. So we want to replace that microstructural model with some homogeneous model. Homogeneous means that there is no fibers in that reference volume. So we started from this equation, which says that characteristics of the process have to be the same for both models. So we have to get same curves of mass release for both models, and that is validation that those two models are the same, basically the same. So Professor Kovic introduced these two coefficients, these two equivalent values. It is equivalent value of diffusion coefficient and equivalent value of distance from the surface. And if we found those two parameters, we can replace microstructural model with continuum model. For us, it is very good because if you want to model microstructural model, we need to have a lot of finite elements inside that reference value. If we replace this microstructural model with continuum model, we replace, for example, 1000 equation with 2 or 8, because we have just 8 nodes for this finite element. So we introduced these procedures which is used for calculating these equivalent values. For example, the first step is that we, for this selected reference value, we assume that there is no surface effect, so there are just fibers in the system. We just have porosity. So for the system without surface effects, we first calculate the release curve, and then we are for the same model, continuum model without fibers, we are how to say fitting this debug in order to have comparison between curves of microstructural and continuum model. Then third step. Now we are using the full model with surface effects, and we calculate, again we calculate these curves for this microstructural model, and we have to now again to find this h, which is equivalent distance from the surface. So fourth step, in order to get good comparison with the microstructural model, we started from this equivalent debug, which we calculated from the second step, and we fit this equivalent distance in order to get good comparison with some tolerance between microstructural and continuum model. So these are just some of
1 minute to end.
Okay. These are just some of examples we provided in order to see if these equivalent parameters are good, and we changed for example, the volume of our reference volume, and as you can see, these parameters are not changing too much, and also we changed the input values, for example, input concentration and input volume of inlet reservoir, and as you can see, these parameters are not changing too much. We also did some examples with 3 examples. The porosity of fibers is the same for all 3 examples, but total area of surface in the system are not the same. As you can see, we have different surface area, and this equivalent distance from the surface is different. For example, if for the smallest area, this h is biggest, which means that the diffusion is less constrained. This is just some animation. So first we do modeling of this system. We have some computer-aided design software for modeling this microstructural model. What we can do in post-processing, we can see the fields of concentration, mass fluxes in our models. We did some some research with agarose pouring gas. So we use some picture from electron microscopy. We are trying to reproduce fibers from those pictures, and then started our FEM calculations. In Houston, some experiment regarding this topic was done, and we are now trying to to get the same results in order to validate our model. So conclusions. What is our goal? That we are trying to apply our numeric homogenization procedure to some various internal structures of any complexity. This presented methodology is supposed to be applied to some very large system with a different complexity, with multiple molecule types, multiple surfaces, and various media. And I will just, in the next two slides, just show what are our current research. So we have some blood vessel capillary in the system, and we are trying to explain and to see how these, for example, these molecules, therapeutic particles, are going through the wall, so we can model the network of the fibers which is inside the wall, and then we want to know the mass release through these fibers networks. Also, if we have some mammary glands, experimentally it showed that after some time there is communication between two mammary glands. So we try to using this picture to create our FEM model in order to see diffusion process and to have better insight of this diffusion process. Okay, that's all. Thank you.
Thank you very much, William. Questions for William?
So basically, if you want to make a model for a specific molecule, what are the experimental data that you need? I mean, you show here you need the structure of the matrix, right?
Yes. For example, we was thinking about imaging. So, for example, if you have some good image about of your system, we will try to do our FEM model.
But in different time points, right?
In different
time points over time, how it changes.
Yeah, during the time. Yeah, of course. Yeah. So we want to have better explanation of this diffusion process through this complex media. For example, you have extracellular matrix. A lot of drug particles are going through the SEM to the cells, and we are trying to get better explanation of this processes.
It depends also on the molecule itself.
Yes. For example, if you have smaller molecules, diffusion is easier.
It depends on the size of the molecule.
Yeah, it depends on the size of of course. I have one slide. I have, for example, two different molecules. I have doxorubicin, which has smaller diameter, and I have liposome, which has higher diameter, bigger diameter. So I have these two scaling functions. If you can see from those two diagrams,